Yeah, hi everyone. Welcome to Pandas 7. So, this session is about encoding and decoding. This is, you can say, this is optional um, because we'll be going really deep into some uh, computer science fundamentals, like how computers represent um, characters, how you are seeing this text, how the images are displayed, how the video is displayed. The you can say the underlying representations. So this is about encoding and decoding. Basically, we'll be looking at those two methods, primarily the ones which are series.str.encode and series.str.decode. So we'll be looking at what is encoding and decoding, then common encodings that are present on the like in every operating system, then how to handle errors, then we'll look at binary data, all of this stuff. Again, I'll cover each and every one of them. So the first thing, as I've already discussed, I think in my previous or the previous one, what encoding and decoding is in general. So basically, if I have some human readable text like hi or hello or something like that, I want the computer to understand my text. So as you know, computer only understands things in binary, and its higher level applications have their own representations. So you have to speak in their language to communicate and make it do the stuff that you want it to do. So to just give you a very like an analogy, like if suppose two people are there, like person 1 and person 2, and this person speaks, let's just say, Sanskrit, and this person speaks Japanese, right? Now, if I want to communicate to him, my language he will not understand, and I won't understand his language. So we need some sort of a translator here, and that is where let's just say Sanskrit to Japanese conversion is the encoder, and if I want to understand what he is saying, then I need a decoder here, which is the Japanese to Sanskrit, which is you can say the decoder, right? That is that is basically the general analogy. Let's just see. And the encoders, like you can say, there are different encoders, like or rather there are different encodings. Basically, text, how the text is represented. So basically, text is represented in different ways. Let's just see. Yeah, let's go to the next one, which is common encodings and how characters are stored. So basically, if you see the way computers work, you have like the base reality, which is the first layer, which is your electrical signals, right? So these are the binary states, like it's either on or off, right? And then to represent this on-off behavior, you have the binary representation, which is your 10 10 10. These are basically those electrical states that are represented this way. Now, this binary representation is too long and not very human readable, right? So we came up with another abstraction which is basically rather okay. The next set is bytes. So this is not exactly abstraction. This is sort of a way to chunk these binary representations in 8 bit format. So like you have 8 bits, 8 bits. So you can say, let's just see. So you have this text, right? So instead of me reading it as WHAT, I have made a representation called what. So the what is your the sound what is the, you can say, is the byte representation of the, is the byte representation of the binary rep. So instead of me saying reading this word as encoding, I'm just calling it encoding. It's just a quicker way of representing those set of words, those set of characters. So byte is exactly that. You can say it's in one sense, that is what it is. A byte is composed of 8 bits, right? And then now even this is also not very human readable. So to make it human readable, we made further abstractions like hex and base 64, something like these two. So hex is composed of 2 characters. Each byte is composed of 2 characters. So which is basically 4 bits is half a byte is one hex character. So it ranges from 0 to 9 and A to F, right? So this is again another short form representation of bytes. And then you have base 64, which is another abstraction. You will have again some words. You will see base 64 encodings if you have used APIs, right? You have some, say, the auth tokens. You will generally be converting them into some sort of base 64 or something like that to send it. Hex, you will see this in MAC addresses and others. So these are again very low level implementations. Obviously bytes and binary are the lowest level, right? And then if you go higher, and we are, again, these are also little too complicated for us to operate. So we have abstracted further to represent characters in something called encodings. These are basically, you have 4 very common encodings, which is one is ASCII, one is Latin 1, or this is also called as ISO something 80 something, and you can also call this as extended ASCII. Excuse me. And then you have there is something called CP1252, if I'm not wrong. This is a Windows based thing, which is essentially the same as extended ASCII, right? And the 4th one is the latest one, which is UTF-8, which is basically Unicode, right? So ASCII is basically the you can say the first implementation, and it ranges from 0 to 127, total 128 characters and encodings. So this has a 1-to-1 relationship. So basically what it means is the 1-to-1 means let's just say the character ASCII decimal value is 1 and its encoding is also the same, you can say. So if suppose it is 1, this is also 1. It will be more clear when I show it to you in the demo. So ASCII has 1-to-1, even Latin also has a 1-to-1, but Latin ranges from 0 to 255, if I'm not wrong. So basically 256 characters, and the same one-to-one encoding. So if there is a character A, then the encoding is also A in it. And then CP1252 is also same. It's essentially the same as the Latin or extended ASCII characters. And then you have Unicode, which is the complete version, or rather the massive character set. This is not the same as encoding. So the character decimal value is not equal to the encoding. UTF-8 has a variable 4-byte length for every character. So the while ASCII has fixed 1 bytes assigned to that, right? ASCII, Latin, these all have fixed 1 bytes, while UTF-8 has 4 bytes assigned to each character, or not a fixed 4 byte, but a variable 4 byte. So it can be anything from 1 to 4 bytes, right? What else? And okay, by the way, the range of UTF-8 is large. So this is the superset. UTF-8 is the superset of all characters. So this has every possible character that you can imagine or that you see on your laptop or your computer. Everything that's available online, every character available online is present in this. So you have like these special characters, you have question mark, you have again, question mark is also available in ASCII, but everything you have like Japanese or Sanskrit or whatever, something, you know, every possible character is present in this UTF-8, and it almost has 300,000 plus characters, and if I'm not wrong, more than 1 million as well. More than 1 million are available, and let's see, and like I said, it's not a one-to-one mapping. So encoding the character decimal value, decimal is not equal to encoding coding for UTF-8, basically Unicode. So that is yeah, these characters are again the use cases are, so UTF-8 and all, these are all for higher level applications. Like you see this Notes app, all these use UTF-8. Like pretty much all modern applications use UTF-8, right? Because they have to support all possible characters. Every language that's existing or that has been converted into online text format is present in this UTF-8. So all major new applications use this. ASCII, Latin, and in fact ASCII especially, Latin, CP1252, these are all for legacy systems, or if you need some memory efficient like memory efficient processes or applications like network based where memory is a constraint. So these have fixed 1 byte, right? So in such scenarios you can use ASCII. Latin is for slightly higher, like since this goes from 0 to 255. It's for slightly higher applications, you can say. Yeah, that's based. So all these character sets, or rather characters and encodings, are used as per the need, based on based on the application, based on how low level you want to go, how memory efficient you want to go, or how based on the set of features, you can say. Since UTF-8 has a large number of characters, it literally covers everything. So all this is supported. You can use this for every possible application, except when you have some memory constraints or something like that. All modern applications, you can say. Then let's see. Right. So this is basically what encodings are, what their memory is, what their use cases are, and memory limitations. And so basically, these characters are all stored in either bytes. Again, you have different conversions, like you see all these conversions. Based on the need, these characters will be stored, but the base level, as we saw here, this is the hierarchy. So let me just write it clearly. So you have binary, right? Then you have byte arrays or byte objects. That's the next level. Then you can either store it in hex or base 64. You will see these in databases, right? This is in MAC addresses. This is the fundamental memory storage. So that is like the base level, which everything is stored. All applications, all every possible, like every storage is finally gets converted to this only. So then even higher would be the encodings, which is your ASCII, UTF-8, etc. And then even higher would be your strings, then which is basically your characters, images, video, audio, etc. So this is the hierarchy. So let's get into error handling. Okay. Before that, we'll see a quick demo on how this our encoding decoding. Even though we already saw this in the previous class. So let's do the usual ceremony again. Pip install pandas. Although I don't think we'll use numpy, but anyway. Import pandas as pd. Import numpy as np. We actually also need to import one more thing. But I guess we can do that as and when necessary. Okay, we have done our imports. Now if we will quickly construct a data frame. We'll make a quick data frame. So we'll make a small one. We don't need, we won't be operating on large data right now in this, we'll be doing that here anyway. So I'll just create a small data frame, pd dot data frame characters. I'll say I will use maybe a special E or something like that. I'll use this E. By the way I'm getting it is just on Mac, you just have to long press the key to get those options. Maybe I'll introduce an emoji. To again get the emojis on Mac, you just have to double click the function key. Right, just these three, I think that's sufficient. Okay, so we have our table. Now, if we do encoding, so all we have to do is get the chars .str. We have to access the string object, and then we do a encode. And if I do a UTF-8, what you will see is you will see the same thing, or rather not the same, you will see the bytes. Encode gives us the bytes. Now if you see these are, you will see this is a byte string. You have a B prefix before the double quotes or the single quotes, whatever the string notation. So this is the byte notation that we saw here. This is this level. We are at this level right now. So if I want to get back my data encoded, so if I want to get back my data, I just have to do dot. 1 second. Let me just assign this tf encoded. So we have our encoded. Now if we do a we'll do a decoded column. Decoded would be the same as the characters. We should get the same as characters. So we will use tf encoded. We'll use the encoded column. We'll use actually we don't need to use the string because decode method is only available on bytes. So we do a decode and we'll set the same key, UTF-8. So this UTF-8, all these encodings are like standardized keys that are available. So in the last class, I think I discussed about an example called substitution cipher, right? So suppose if I want to send a message to my friend, say something like hello, right? And I want this to be secret. I don't want anybody in between to know that I'm sending this exact message. So what I will do is I'll create a one-to-one mapping. I'll say H is A, E is B, L is C, L is again C, and O is D. So I will, this is my key. So I'll create a separate key and I'll pass this message A, B, C, C, D. This is some random, this doesn't make any sense, right? So so when this goes to my friend, like say the person 2, he will receive this message A, B, C, C, D. Now he wants to know what this means. He needs the exact mapping, the key. So he has to know that A means H, B means E, C means L, right, and D means O. So this mapping, so this key is what this UTF-8 is. This is like a standardized key that everybody knows, you can say. So basically this UTF-8 and all these encodings are like the standardized keys. So if I do this decode, now if I check my data frame, 1 second. Series object has no attribute decode. Do I have to use str? Okay, I still have to use, okay. It is a byte string, so I guess we still have to access the string object. So when we do a decode, we'll get back our original characters again. But yeah. So I guess it's considering that way, but decode basically, you can only access decode on bytes. So yeah, it's byte string, it considers it as byte string. So I guess that's why you need the string object accessor. So that's fine. So this is our, this is what we discussed before as well. Now what we are trying to do is error handling. So basically when dealing with data, like you can get, so we discussed different types of encodings, right? So you have, generally you have like different encodings like, oh shit. Okay, let that happen. So generally you have different encodings like UTF-8, exactly what you can pass. Then you have Latin 1, you have ASCII, then you have CP1252. These are the 4 common ones. Yeah, so since the UTF-8 supports like over 1 million, right? So its decimal values will also be in that range. Latin is 0 to 255. 255, ASCII 0 to 127, and this is also same as Latin. So what happens is, if suppose there is a character set from UTF-8, right, and you are trying to decode it with ASCII, it will fail. So something like, we'll use the same example. I'll use df chars. And if I do str.encode, if I try to encode using, let's say, ASCII, you see what will happen? It will throw an error, Unicode encode error. ASCII can't, codec can't encode character XE8 in position 0. Position 0 is this one. Wait, position 0? Ordinal not in range 128. 1 second. What is A? What is A? Oh, it's not in range. Chars str. No, it's not. In position 0, ordinal not in range 128. No, I guess it's throwing that for 1. Yeah, it's throwing for. Okay, it's throwing for position 1. Fine. It's not for steer. So basically, the reason why it's throwing is it understands A, because A is within A is ASCII. A uppercase A is 65 and it's within the ASCII range. So if you see, the ASCII range is 0 to 126. 126. Oh, okay. So okay. So there are 127 characters. It's not total 127 characters. So 0 to 126. Yeah, and if you see this, this E is part of Latin. It's not part of. It's part of ISO. So if we go to the acute, it's called acute accent. I don't think it's even part of Latin as well. 1 second. Okay, so you can see here Latin has an extended see ISO and Windows, right? 1252. Did I write the same? 1252. Okay. Extended ASCII goes from 128 to where is it? 255. Basically, total 256 characters. I think E should be part of this one, if I'm not wrong. Yeah, see, there you go. E is part of this one, 233. So if we do a, so if I do it with Latin, it will throw an error for the emoji. So if we try to do for, if I take from 0 to let's say, it will process properly. So I'm taking the first 2 records. It it encoded them properly. The third one requires a UTF-8, which is the Unicode, because this is an emoji. Emojis are part of the Unicode. So for that, if we do UTF-8, UTF-8 is the superset, right? So it has ASCII, it has Latin, it has everything. So it can encode all the three values. So to avoid errors, so we are talking about error handling, right? So if we look at our documentation for encode, so there is a errors which defaults to strict. So there are three error you can say three error labels. First one is strict, second one is where is that? Yeah, other possible values are ignore and replace, right? I guess this is not the correct documentation of it. v.series.str.encode. Okay, there you go. So we have encoding option, which we just gave UTF-8, and the second option is errors, which is a string, and the default is set to strict. So strict means it will throw an error if it is not able to, if it's an incorrect, or rather if the text is, if the text cannot be encoded with the specified encoding. The other error values are okay, this is also not giving the, yeah, I guess this one was only better. Okay, so the other two are ignore and replace. What ignore does is it ignores those characters and like encodes whatever is possible. So you'll have a data loss here, you'll miss some data here. And the replace is again, this is also in one sense data loss, but what it will replace it with a question mark. Whatever data it could not encode, it will replace it with a question mark. So again, in one sense it is data loss, but you will know that you lost some data there. So let's see. So if I do ASCII, and if I, this is my encoding, and if I do errors ERRS equal to, if I give it, so currently it is strict, so strict will throw an error. Now if I set it to ignore, you will see here the it just gave empty, like it completely discarded all the characters it could not encode. And if we set it to, what was the third one, replace, you see it set it to question mark. So that is how you see the errors. So that's basically how error handling works. Let's look at the third one. So reading binary data from files. So this will require a new import called import base64. So we are at this level here. So we are at this level right now. We are doing this. Oh shit. We are checking this one. So it's just a small demo. We'll see how base64 works. So what we can do is we can create the same data frame, but I'll add some encoded text in this. So base64 accepts bytes value. So since we have our bytes here ready, we will take the same thing. So instead of this one, I will take this. Instead of that, I will take this one. and I'll take this one. A is A, so that's our standard. So as you can see, ASCII has a one-to-one mapping. So that's what I mean one-to-one. So the encoded and decoded values, or rather the original character and the encoded value are the same, exactly the same. But that's not the case for okay, wait 1 second. Let me do an. It should be the same for Latin as well. Let me check the first two. So 0 to 2. I'll set it to Latin 1. Okay, so it's not exactly the same for Latin. Okay, it should be the same, but let me see 1 second. Zero to 56. Okay. Let me run this once again. In my data frame, I'm setting the Latin version. Oh, 1 second. I'm checking the wrong one. Wait, I'm checking the wrong one. Characters, we will set it to Latin 1. We'll just check it on the first two characters. Sorry, first two records. Okay, so I guess it's not the same. Let's check this one. So pound. No, that's what euro, I guess. It's not the same. Okay, it's not the same. Yeah, I guess that makes sense since these are all special characters. I guess they wouldn't be the same. Yeah, okay, my bad. It's not the same. So only ASCII has a one-to-one mapping to the after encoding. Only ASCII has a one-to-one mapping. So where were we? Yeah, so we were looking at reading byte data, or sorry, we're checking binary data from files. So this is the base 64 use case. So if we look at our data frame, we have our it's called these bytes. We have our byte data. Now if I want to encode these bytes using base 64, so you have to do something like df bytes. Okay, let me not give the same name. Byte. There's an object called bytes. Let's not give the same name. Say bytes. If I access the bytes, I have to use the string object because that's a byte string, and excuse me. um, right, then we do a we have to apply lambda x for every x value. I'll use the base 64 dot b64 encode, and then I'll pass my value. If I do this, now you will see string methods object has no attribute applied. How about this? Okay, there you go. There is our base 64 encoded value. I will assign this to df b64 encode. Create a new column and I'll assign this. Now so there is our table. Now if I want to decode this data, what I will do is I will get my encoded base 64 encoded value, and I will do an apply again. I will do a lambda, and I will do a base 64. I'll get the B64 decode. Now you see we'll get our bytes back again. Now if I want to get the original text, right? If I want to get the original text, then what I have to do is I got the bytes, right? Then I do a decode, which is our inbuilt decode method. So this works on the bytes, right? So we do UTF-8 decoding. We'll see what happens, and we get our original result, right? That is how this thing works. So let's create new column, B64 decode. It's actually not B64, it's total decode, UTF-8 decode. And there is our result. So that's how we handle this one, reading binary data from files. Let's get to the next one. So all these conversions, again, we are doing these conversions because the data that we collect from the internet or documents or whatever sources, we might have multiple data sources, right? And the character encoding might be slightly different from all those sources. So it's just a nice to know thing. So yeah, that's the primary reason, because when we are doing data cleaning, and we are probably web scraping or getting the data from files, we might see data that's completely messed up, or that's in a totally different encoding. So that's why it's good to know these things. But anyway, in today's era, we don't have to particularly remember this. It's just good to have this in the back, the back of our minds. We have ChatGPT and all other things to aid us, so it's not necessary to remember. It's just good to know that these things exist. So that's why this class is optional. We don't necessarily have to know this in detail. So get byte object from string or character. So this is our first scenario, right? So if you want to get the bytes from strings or characters, so let's say I have hello, I just have to do encode, and we'll do our standard UTF-8. So we have our bytes, right? if I use some special characters, right, like something like this, then I'll get some hex value, some byte values. These are basically what encode gives us is bytes. Now, if we want to, let's go to the next one. If we want to get the ASCII value of character. So, if I have a character, say H, if I want to get the ASCII value 72, if we verify this, H is 72. So this is the decimal value. ASCII value, it's the decimal value of the character. So we are currently at this level. We are operating on this level, right? And if I want to get the character back again, so I have my decimal value. Now, if I want to get back the character from the decimal, we just have to use the CHR method, and that will give us back our original character. Let's check the next one. If I want to get the hex code of byte object, so if you remember this hierarchy, hex is the higher level representation of bytes, so we can get it from the bytes. So all I have to do is, if I get this one, I just have to use the dot hex. So from the bytes, I'm calling the hex. I'll get my hex value. Then what is this? Get byte object from hex string. So this is our hex string. So let's call this H, right? So if I want to get the bytes back from hex, let's say, what do we do? I think we have to do H. Yeah, we need the bytes object, bytes from hex. This will give us our bytes back, right? Just to verify, we'll do a decode, UTF-8, and there you go. We have our original string. So that's how you get the bytes. That's how you get the bytes from hex. This is the bytes object. It's the reserved object in Python. Then let's go to the next one. Okay, by the way, if suppose you end up creating a variable, like say bytes equal to something, you assigned something like this. Now if you call bytes, bytes, it will give that value, right? So in order to revert it back to the original functionality, you'll just delete bytes, then bytes will get back to the original, it will refer to the original one again. Let's get to the next one. Get original string from bytes. Was it this one or hex string? Is it? Okay, yeah, this one. Get original string from bytes object. Yeah, that's our decode method, right? So we have encode here, and we do a decode. We saw this already. So that's the get original string from bytes object. Then we convert byte to binary value. Okay, so we'll take we'll take a small example. We'll take this itself. we'll take a small one like E. Now we have our bytes. So these are bytes. So we can actually iterate on these bytes. So if I want to get the binary value, we have to use the bin method. Bin accepts a byte. Again, if you remember this hierarchy, this one. So we are currently trying to get the lowest level. Let's say, so we have to iterate on this value. So let's put this as, let's call it as bytes. And what we will bin byte, bin, let's use B, let's not use the reserved names, for B in our bytes, S. So if you see here, it will give us our binary array, but it has a prefix. It has a prefix 0B. We don't want this prefix, right? Let's get rid of the prefix, which is, so from 2 characters, we don't need those 2 characters. And we got our actual binary values for each of those bytes. Now, one thing it's important to remember, binary, when we use the bin value, it does not always give us 8 bits. So a byte is 8 bits, right? So we need the byte value to be exactly 8 bits. But if we use, say, suppose if I have, if I take the binary value of 4, it's only like 3, length 3. It's only 3 bits, right? 2 power 0, 2 power 1, and 2 power 2. So if we look at the value 4, the value excuse me, so the value 4 is giving us 1 0 0, right? It's basically 2 power 0, 2 power 1, 2 power 2. So you know, right, we don't consider the 0 values. So 2 power 0 is 1, 2 power 1 is 2, and 2 power 2 is 4. These 2 are not considered. So that is how we get 4. But these three are 3 bits are not a byte. 8 bits is a byte. A byte is 8 bits, right? So in order to get the actual byte representation, we always have to make sure to pad it with zeros to the left. So we can either do a z fill. If we do a z fill 0, are just 8. Oh, wait. I think I was giving a. Yeah, there you go. We can either use. Okay, R just, we'll have to first of all trim the first 2 characters, because that's not what we want. And that's our actual byte representation. So 4 in a byte representation should be something like this. So actually zfill should also work. 1 second. Zfill, I think I should give a string character instead of. No. Zfill, what was that? Is it zpad or zfill? Zpad. No. Zfill. No. Okay. Okay. Anyway, this is not so important. We can use rjust anyway. Rjust is perfectly fine. It is used for filling the string with the leading zeros. So if you look at the documentation for rjust, interesting. Why is it not giving? Okay, I think I have to use the string. What is it? str. Okay, there it is. Wait, if I use str zfill, there you go. Okay, zfill is also there. Zfill pad a numeric string with zeros. So why was it not working then? Dot zfill are just I want 8 and I want them to be filled with zeros. Okay, I don't know why this is not working, but add a numeric string with zeros on the left to fill a field and given. Okay, I don't know why zfill is not working, but anyway, we can use rjust. So if you see the documentation, rjust takes a width which is the size the string should be. It's the fixed size the string should be. We are giving it 8, and the fill characters, I want the leading characters to be filled with 0. So it's right justified. So that is what this is. We can just use rjust. It's fine. So we'll have a fixed length of 8 because a byte is 8 bits, and we'll fill it with zeros. So that will give us our binary value. So since here the byte values are 8, so these values are 8 bits long, so we don't necessarily have to do it, but just to be on the safe side, when we are doing this operation, it is good to just do this by default. It will remain the same. If it's 8 bits already, it will keep the 8 bits as it is. But if it's less than 8 bits, then it will fill the other values with 0, other bits with 0 on the left, leading 8 on the left. So that is how you get. Wait, what is the thing? Convert byte to binary value. So that's our binary array. Now if you want to get a binary string, which is the next one, so convert byte array to binary string, what we have to do is simply do our join. So we'll use the same thing, and we will use a join. We'll join this with space dot join. We will join this value. Okay, 1 second. Okay, not join here. Okay, 1 second. This is our list. So we want to join each of the values in the list. Okay, let's call this L. So we will join. Wait, what does join accept? Okay, it accepts the list. Fine. Okay, my bad. Yes, we are trying to join the list. So we will join this with a space. We will join. So each of these elements we will join with a space. So it will be this space this dot join L, and we have our binary string, right? So that's how you get that. Let's go to the next one. Get byte object from binary string. So now we want the bytes back from this string. So what we have to do is we'll have to split it, right? Let's call this ls. Now I want to split this. So ls dot split. I want to split at the space right here, right? Let's see. So there you go. We have our binary array back. Now get byte object. Right. So bytes will accept a bunch of int decimal values. So we'll have to first convert this binary values into decimals. So what we can do is, let's call this BL, and this binary list I will convert to ints. So binary value to base 2. So this int, this 2 is base 2. Here this is base 2 for B in BL. So we are iterating over this list. Now let's see what the thing gives. It gives our decimal values. Right, now all we have to do is, again let me just show you what int has. You see here, int accepts the value and we can set the base. By default base is 10. Right now we are converting the base 2 because it's binary. So yeah, what are we doing? Get byte object from, right, so this is our decimals. So decimal list, this is our decimal list. Now all we have to do is get the bytes object and pass our decimal array and we get our bytes, right? We can verify this using decode, UTF-8, and there you go, we have our character. So that's how you get the binary, get the bytes from binary string. Let's get to the get ASCII value from binary, ASCII. ASCII value from binary. Yeah, it's basically the decimal. We just saw it here, right? So, so if we take this binary value, let's see. Yeah, so we just have to do the int function once again. Int method, we take the binary value and we set the base to 2, which is our ASCII value, right? So if we check the character, it's giving us this is the character. So you see here, this is composed of this and this, so it's not exactly, we won't get this E. This is a accented E. So, and accented E has 2 byte values, and these are two. So these are 2 binary values. So we are taking only one of the binary values. So that's why you are getting this character, right? So let's look at the character in the documentation once. Okay, it's considering that as a interesting. Okay, good. So this is 195 beyond ASCII, so we'll have to look into the Latin section. There you go. That's the character, right? Let's go to the next one. Now we are getting into data cleaning and validation. Sure. So this is the scenario where we'll try to emulate data coming from different sources, right? And how to handle those values. So let's take the same similar data frame. Actually, we'll need the byte values as well. So let's take both of them. We'll construct the data frame. Characters and their respective ASCII values were, their respective byte values. So there it is, bytes. And Okay, actually, since we are trying to emulate multi-scenario, I think let me just do this. I'll take the simplest value, CAF. Yeah, instead of these, let me take this one. I'll use the same for all, and I will decode in different, rather I'll encode in different formats. Encode, first is UTF-8, then we'll do a Latin one, then we'll do CP1252, which is our Windows. Excuse me. And what was the other one? Yeah, the final one was ASCII. Okay, let's keep UTF-8 at the last because that's the superset. Use ASCII first. Then let me, I think we'll go with this one. Okay, it doesn't write. I forgot. We'll set the yeah, that's fine. Let's see. We'll use these just to see how error handling works. Use these 4 formats. Actually, we'll do a base 64 as well. Wait. I guess let's not go that far. That's the third one, and I think that will be empty. The bytes would be empty. Let's use a base 64 one as well. So cafe. So cafe encoded UTF-8 would be this one. So we will do base64.b64 encode. I'll encode these bytes. Get my encoded value. I will set this somewhere over here. Okay, actually this should be here. Since that's the ASCII, now we will set the encodings. CENCODING. Encodings would be, our first one would be SCII ASCII, then the second one was Latin, third one was CP1252, fourth one was okay, I have to create one more here. 1, 2, 3, 4, 5. Right, so fourth one was UTF-8, fifth one was base 64. Okay, so we have our data frame ready. Oh, sorry, we didn't pass the data. Okay, so we have our data frame ready. Now what we will do is we'll try to we'll try to decode this. So we can do something like df dot apply. We'll do an apply. We'll pass our function. We'll create the function def func. Pass the data frame. It will get the data frame as parameter. Now we want the let's create our different columns. CHRS. This is our chars column, which is df. I don't think this is necessary. We'll operate directly anyway. Okay, so we are operating on the per row. We are operating per row, so we should set it as axis 1 horizontally. Right, so we want the characters. So df characters dot and okay, wait, we have our bytes already, right? So we want to decode this. So not characters, then we'll set our bytes dot decode. We are trying to decode as per the encoding. This will throw an error at base 64, but that's fine. We'll see. df encoding. So we are operating per row. If you remember how axis 1 works, so we are fetching the row completely. Right. Each row has column 1, column 2, column 3. So this per record, we are operating per record on each value. Yeah, so let's yeah, let's see what this gives. Yeah, it's throwing an error. It's saying key error encoding. The above exception was the direct cause of the following exception. We have a list like key check indexing error will reach. What is the issue? Oh, we are not returning, is it? Key error encoding. Oh, sorry. Okay. Right, base 64 is not text encoding. Use codex.decode. So when we have errors like this, or rather to avoid errors like this, we do a try catch, or rather try except in Python. We'll wrap this under try except. What is the exact exception? I guess it's Unicode decode error is the exception, but I'll just use a normal one, exception. If it throws an exception, we'll just return an empty string. Let's check now. So there you go. It threw an exception for base 64, so it's just returning an empty string here. For all others, it properly decoded, right? Now, in order to handle base 64, we can do something like if it throws an exception, then we'll say base 64 dot b64 decode, CECODE, and then we pass our the byte value. And now it will handle this, right? Either this way, or we can do something. We can just put an if statement, because we have our encoding column, right? So we could say if df encoding equals base 64, Then we return base 64 encoding. Else we return the other encodings, right? This will also work. Wait, what is the 0th column? Sorry, what is the 0th row? Right. So 0th bytes is empty, right? So it's the ASCII value. So that's correct. We didn't give any bytes for that. So we can just give something like this, and this will handle it just fine. So that is one way. Now suppose you don't know what. So here we know exactly what the encoding is for each of these strings. If we don't know what the encoding is, we can do again, we can do the try catch method, right? So try this encoding. If that doesn't work, continue. So we can pass in all the encoding values. Excuse me. Something like for encoding in df, we can pass the list of encodings, and we can do a try except here, try cpt ception, and then we return actually we continue. We keep continuing until it handles the value, right? So you can say something like df encoding, we pass our encoding so let's see what this will give. Oh, we're not returning. Okay. Still none. df bytes decode. So the first column, it's getting the bytes, it's trying to decode using the encoding. This should work, huh? Why is it not working? Decode. Let's debug this once. Print so it's checking hello. Hello, what is A? Print bytes is hello, and encoding is A. What? What is an A? Encoding is A. For ASC, what is all this? Oh, okay. Oh, okay. Right. So I think it is. Okay, okay, okay. Let's call this DFF instead of this one. We are trying to get this, get the entire list here. We are trying to iterate on the entire list, not on each of the character of each of these strings. Right? I think this should work now. There you go. Right, so so it properly handled everything. Now the base 64 one got passed as it is. So for that we can say if there is an exception, we can just pass our base 64 dot b64 decode. Yeah, actually that will also not work because all the other encodings will now pass to base 64, which becomes another headache. So we'll have to use another try catch. So yeah, if it is base 64, I guess we'll have to handle separately. We'll have to filter those out. But yeah, so basically this is how you can handle this. And in fact, just to make it more robust, we can actually check if the values are an instance of bytes. Only then do the decode, right? Since decode only works on bytes, so we can do something like if is instance, I will get my DFF bytes. If bytes is an instance of bytes. So this, if these, we are checking if this is actually a byte value or not. If it is not bytes, then we'll simply return. Right, so that's how we can make it more robust. So that is basically how you can do data cleaning and validation. Yeah, so this is the example. So the basically again the use cases when we are fetching the data from web scrape data, or we are combining multiple sources into a single one, like files, like API data, or the data from databases. We can kind of do this. We can do something like this. One of the warnings you can see is if you see data like this, like some gibberish like this, then it's like a clear sign that okay, we need some encoding. Or if you keep seeing question marks, right? Suppose if I set this one, okay, if I set this one, and if I set the errors to replace, if you see something like this question mark or something like that, at that time you will know that you need encoding. Or if you see that Unicode decode exception thrown, all these are like warning signs where you'll have to use decoding to normalize the data. Now let's coming to normalize text with Unicode points and vice versa. So basically normalize means it's as the name sounds, we are trying to flatten or kind of standardize the format of the data. So suppose right now what we did is standardizing. So this decoding process is normalizing. We are converting all this messed up text, right? All this byte values, all different formats. So if they are in hex values, if they are in bytes, if they are in this one, we are trying to get all of them to string. So that's what normalizing basically is. So in this scenario, with Unicode points and vice versa. So here we have to import a new one, which is called import Unicode CODE data to operate on this. Um, yeah, so we do Unicode data dot normalize. Suppose we'll take this example. This is like kind of perfect here. There are. Let's look at the documentation. You see here, it takes two arguments, form and Unicode string. Unistring is the Unicode string. So form is any one of these four. We'll only look at NFC and NFD. I think those two are sufficient. So NFC is canonical decomposition and composition. NFD is canonical decomposition. Forget the names. Basically, what it means is if you suppose have caf A, so you have that accent at the top of E, right? For this E, you have an accent character. So decomposition, it splits that special character and this E separately. Recomposition, it merges these two characters. Just think of it that way for now. So I'll do a NFD, and my Unicode string is I'll suppose I have a Unicode point. Now this is a slightly different one. Unicode points. So if I see my this. Yeah, so let me just take a character called acute accent. Yeah, there it is. So you see this accent character. Suppose I give this. So sometimes you might get data from when you web scrape, you might get data something like this. Caf, something like this, right? Now if I want to normalize this, I use this method, normalize. Okay, so CAFE, if I use that E, then it will attach that Unicode point, it will attach that accent to this E. Now if you try to extract the last character, let's see what it will give. See, it gave the accent. It did not give the special character E with the accent, it gave the accent. So to get the special character with the accent, we'll have to use NFC. So we need the composition, the combined version. Yeah, so that's what it is. If I use this one, if I use the character directly, you will see I'll get the E if I use an NFC, and if I use an NFD, I'll get my accent. Now let's go to the next one, which is again, you don't have to remember all this. It's just convenient ways of getting the data that we want. Right? Then we want to convert normalized string to Unicode string. So this is our normalized string right now. NS, let's call it normalized string NS. So we have the normalized string. Now if I want this Unicode point value in the string format, we won't get the exact point directly in this way. We'll get a Unicode string value. Let's see, what do I have to do here? Convert normalized string to Unicode string. I think I have to do something like ns dot decode Unicode space Okay, so I think it is. So it's not. So we are trying to convert the normalized string into Unicode string, right? So the Unicode string is for the accent character alone. So let's fetch the accent character alone. Let's call it AC. Let's get the -1. Let's do an NFD because the accent, we want the decomposed one. We want the accent alone. So now to convert this, we have to use the format. We have to format it to \u, and we get the accent character, and colon, we have to write 04x uppercase, sorry, not here, colon 04x uppercase 4-digit hex character. We use 4x if it is if the range of the characters between 65,000 something like that in Unicode, and if it's greater than 65,000 we use 08x. That's for greater than 65,000. So hex values. So if we do this, okay, it should be ordinal of this one. It should be ordinal. The decimal value of this character, colon 04x, this should give us our, you see here, this returned back as our Unicode point value, Unicode string value. This is not exactly it's still not Unicode point, it's the Unicode point value in string. Now if we want to convert the Unicode string to Unicode point, we'll have to do something like let's call this US is called this US. So we do a Unicode string dot, we encode it first to get our bytes value, and then decode it with a special Unicode escape sequence, SCAPE. Let's see what the result is. So you see we have our character back, right? Now in order to attach it back, we do a Unicode data dot, we do a normalize again, and this time we do a Unicode decomposition, NFD. We'll do an NFC, anything, and then we use the character CAF, and then we get our Unicode acute accent. This will give us our cafe. So that's how you do it for this one, and that's all there is to it. I hope it was clear, and I'll see you in the next one.